Port numbers. Port numbers are 16-bit non-negative integers ranging from 0 to 65,535. These numbers are abstract and do not rely to anything physical. Instead, each IP address has 65,536 associated port numbers for each transport protocol that uses port numbers. Most do, and they are used for determining the correct receiving application. So the IP address has an associated 65,536 port numbers for each transport protocol that uses port number. So most transport protocol uses port number to be able to map the physical the IP address. So IP address has 65,536 associated port numbers for each transport protocol to be able to activate that on the corresponding application. For client or server applications, which we will discuss later, a server first binds to a port number, and subsequently one or more clients establish connections to the port number using a particular transport protocol on a particular machine. So the clients establish connection using the transport protocol that was initially binds or initiated by the server. So it is initiated from the server's side first before it can be established by the before the client can establish connection to that port, like a TCP, etc. Standard port numbers are assigned by the Internet Assigned Numbers Authority. The set numbers is divided into special ranges, including the well-known port numbers 0 to 1023, the registered port numbers 1024 to 49,151, and the dynamic or private port numbers 49,152 to 65,535. Traditionally, servers wishing to bind, like offer service on a well-known port, require special privileges such as administrator or root access. So before, if you want to bind or to start a service with using a well-known port, it will require a special privilege such as administrator or root access. The range of well-known ports is used for identifying many known services such as the Secure Shell Protocol (SSH), which is port 22, FTP ports 20 and 21, Telnet Remote Terminal Protocol port 23, Email or Simple Mail Transfer Protocol (SMTP) port 25, Domain Name System (DNS) port 53, the Hypertext Transfer Protocol or Web (HTTP and HTTPS) ports 80 and 443. Interactive Mail Access Protocol (IMAP) and IMAPS ports 143 and 993. Simple Network Management Protocol (SNMP) ports 161 and 162. Lightweight Directory Access Protocol (LDAP) port 389, and several other ports. Protocols with multiple ports, HTTP and HTTPS, often have different port numbers. depending on whether transport layer security TLS is being used with the base application layer protocol. So protocols with multiple ports like HTTP and HTTPS actually have different port numbers depending on whether transport layer security is being used with the base application layer protocol. So if it's using TLS, it's using an HTTPS port. If we examine the port numbers for these standard services and other standard TCP or IP services like Telnet, FTP, SMTP, etc., we see that most are odd numbers. This is historical as these port numbers are derived from the NCP port numbers. NCP, the Network Control Protocol, preceded TCP as Transport Layer Protocol for the ARPANET. So NCP used to be the Transport Layer Protocol before the TCP when we were working with ARPANET. So remember ARPANET are before the OSI model. NCP was simplex, not full duplex. So each application required two connections and an even odd pair of port number was reserved for each application. So even and odd pair of port numbers was reserved for each application because it requires two ports. When TCP and UDP became the standard transport layers, only a single port number was needed per application. So when TCP and UDP became the standard transport protocol, the only a single port number was needed per application. Yet the odd port numbers were from NCP were used. So it's still unclear why they choose the odd instead of the even. But that's the reason. It was historical. It came from NCP. The registered port numbers are available to clients or servers with special privileges. But IANA keeps a reserved registry for particular uses. So these port numbers should generally be avoided when developing new application unless an IANA allocation has been procured. So you must not use the registered port numbers at not at all costs most of the time, because you have to procure it or allocate it using IANA because it requires particular or special privileges to use those ports. The dynamic or private port numbers are essentially unregulated. So it's unregulated, meaning it is not secure. As we will see in some circumstances, like on clients, the value of the port number matters little because the port number being used is transient. Such port numbers are also called ephemeral port numbers. They are considered to be temporary because a client typically needs only one as long as the user running the client needs service, and the client does not need to be found by the server in order to establish a connection. Servers conversely generally require names and port numbers that do not change often in order to be found by clients. So the server does not need to know the client to establish connection, and this connection are just temporary. because you're just using, for example, um, this port number for TCP at a certain request, and you usually use other service or other server in the internet for your needs. So it only use case is based on user's usage, and it is abstracted from the user's view. Names, addresses, and the DNS. With TCP/IP, each link layer interface on each computer, including routers, has at least one IP address. Names, addresses, and the DNS. With TCP or IP, each link layer interface on each computer, including routers, has at least one IP address. So at least one IP address are linked to each computer when you're doing a TCP IP connection, which most of the connection in the internet. IP addresses are enough to identify a host. IP addresses are enough to identify a host, but they are not very convenient for humans to remember or manipulate, especially the long addresses used with IPv6. So this IP address could be IPv4 or IPv6, could be multiple in one host, but one is enough to determine which host are we pertaining to. Now it's not convenient to remember it, that's why we have converted it to a name. So we use a DNS or a database. Usually it starts from the top, the .com, and then it slowly um, go down to its category, from the global to the country to the maybe region, etc. But the idea is, instead of requesting or converting your name exactly, it start methodologically um, with respect to organization, from global or from high level, or to all the way down to its details to get to your specific um, IP address. Now in the TCP or IP world, the DNS is a distributed database that provides the mapping between the host names and IP address. So if the ARP provides the mapping in Wi-Fi or in network layer and link layer, Wi-Fi and the IP address, here the DNS maps the IP address and host, and vice versa. Names are set up in hierarchy ending in domains such as .com, .org, .gov, .in, .uk, and .edu. Perhaps surprisingly, DNS is an application layer protocol and thus depends on other protocols in order to operate. So this DNS is at the top, at the 7th protocol. So it depends on protocol below the layer, such as the TCP or transport protocol, uh, in order to operate. Although most of the TCP or IP suite does not use or care about names, typical users, like those with web browsers, use names frequently. So if the DNS fails to function properly, normal internet access is effectively disabled. So the TCP or IP suite protocols does not care about the name. You just need the IP address to be able to interact with it. But if you provide the IP address to the customer, they will effectively won't be able to use it because it's too long. It's too much cognitive load. So chapter 11 looks into the DNS in detail. Applications that manipulate names can call a standard API function to look up the IP address or addresses corresponding to a given host name. So there's an application that convert your IP address to a name, and that's called a standard API function. So that's usually where you register your domain, you where you convert. For example, you have cloud HTTPS from Google Cloud Run or from Vercel. Those could be converted to your desired name. Uh, for application that does not, for web application that does that converts standard API function to lookable name. Similarly, a function is provided to do the to do the reverse lookup. So you also have the ability to reverse lookup using name to an IP address. So that's what this function provides. So some application provides you with this just the other conversion from IP to name to be able to serve to the internet, but others can do the reverse lookup, such as your Google browser. It can pin down the IP address to a name as well. So given an IP address, you can look up the corresponding host name. Most applications that take a host name as input also take an IP address. So most of application that takes this, however, like Google Chrome, Brave, also take an IP address. So web browsers support this capability. For example, the Uniform Resource Locators. So that's actually the what it is called, a uniform resource locator. So our app, in our thesis app, we use this uniform resource generator, so instead of locator, to be able to provide different links, uh, link host name to different clients. So if, for example, the uniform resource locator HTTPS 131.243.2.201/index.html, and this HTTP uh, colon slash slash open square bracket 2001 colon 400 colon 610 colon 102 colon C9 closing square bracket slash index.html can be typed into a web browser and are both effectively equivalent to http colon slash slash ee.lbl.gov slash index.html at the time of writing. The second example requires IPv6 connectivity to be successful. So these are an IPv6 address. So to be able to execute this on web browser, you need to have an IPv6 connectivity on your router or Wi-Fi. Internets, intranets, and extranets. As suggested previously, the internet has developed as the aggregate network resulting from the interconnection of constituent networks over time. The lowercase internet means multiple networks connected together using a common protocol suite. So if multiple networks like from Bulacan to Quezon City to Manila is connected using a common protocol suite, that's what you call lower I internet. The uppercase internet refers to the collection of hosts around the world that can communicate with each other using TCP or IP. So the lowercase internet doesn't need to be a TCP or IP. It's just a common protocol suite. But for a higher case internet, it needs to be TCP or IP, and it is all the hosts connected around the world, or collection of hosts and hosts around the world. So again, N host is a network device, right? The internet is just a network device. The internet is the capital internet is lowercase internet, but the reverse is not true. One of the reasons for the phenomenal growth in networking during the 1980s was the realization that isolated groups of standalone computers made little sense. A few standalone systems were connected together into a network. Although this was step forward during the 1990s, we realized that separate networks that could not interoperate were not as valuable as bigger network that could. So a network that can connect is not valuable. The value of a network is its length, or its scale around the world. So this notion is the basis for the so-called Metcalfe's law, which states roughly that the value of a computer network is proportional to the square of the number of connected endpoints. So just so you know, that net came from like fishnet, interlace fishnet, and work is that putting that lace to work. So now it has been used to describe a bridge or a combination of networks or interconnected system. Now it is being used in computers as well, which is this, a network. It's like a network connected to a network. The internet idea and its supporting protocols, which is the TCP or IP, would make possible the interconnection of different networks. This deceptively simple concept turns out to be remarkably powerful. The easiest way to build an internet is to connect two or more networks with a router. A router is often a special purpose device for connecting networks. So a router, we described that before as routing packets uh, in network layer. Now, another way to view it is a device used to connect networks. So it started from two networks. Now it's connecting multiple networks. The nice thing about routers is that they provide connections to many different types of physical network. That's the nice thing of about the router, because the router is kind of like the Wi-Fi or in the link layer. Therefore, it is abstracting different physical networks such as Ethernet, Wi-Fi, point-to-point links, DSL, cable internet service, and so on. These devices are also called IP routers, but we will use the term router. So these are all using IP. That's the reason why it's TCP IP, because that IP distinguish or allow us to distinguish a host in this network. It allow us to differentiate it. Historically, these devices were called gateways, and this term is used throughout much of the older TCP or IP literature. Today, the term gateway is used for an application layer gateway, a process that connects two different protocol suites like TCP or IP and IBM's SNA. So this gateway now means a process that connect two different protocols or a set of protocols. Two different set of protocols rather for one particular application, often electronic mail or file transfer. So this is the basis of file transfer and electronic mail, connecting two different protocol suites or set of protocols. In recent years, other terms have been adopted for different configuration of internets using the TCP or IP protocol suite. In recent years, other terms have been adopted for different configurations of internets using the TCP or IP protocol suite. So there has been multiple terms or other terms that has been adopted for configuring a small networks that is configured by TCP or IP protocol, not just any protocol, just what we describe as the small internet. So an intranet, for example, is the term used to describe a private internetwork usually run by a business or other enterprise. Most often, the intranet provides access to resources available only to members of the particular enterprise. So the difference with this is the administrative policy in which people can only access these networks. So a lot of networks are actually private. It can't be accessed in the internet. So users may connect to their corporate intranet using a virtual private network. So now it is being done in the cloud. You can create your own intranet or private networks with an administrative configuration. So these are the terms that has been adopted is an intranet, and it is connected using virtual private network. So this is where the VPN came from. In many cases, an enterprise or business wishes to set up a network containing servers accessible to certain partners or other associates using the internet. So again, in many cases, an enterprise or business wishes to set up a network containing servers accessible to certain partners or other associates using the internet. So if you want to, for example, set up or connect with other virtual private networks such as your partners or associate using the internet, for example, such network which also often involve the use of VPN, are known as extranets and consist of computers attached outside of the serving enterprise firewall. Now, it is outside of that private network compared to the internet, which is more inside. So, the difference here is the administrative uh, configuration as well, in which for outside, you have more restricted access than inside because that's your employee compared to the outside partner. Now, we use that for corporate policy or corporate applications nowadays. For example, when you're working in Microsoft, they have some access with, for example, tools with or network with Google or something or anything, you know, application that is outside of their own virtual network. Now, designing applications. The network concept we have touched so far provide a fairly simple service model, moving bytes between programs running on different or occasionally the same computers. So the concept we have touched is more on infrastructure side, but in actuality, it's moving bytes from an actual computer memory to uh, sometimes within the computer itself, but sometimes outside the network, you know, moving bytes from its memory to an outside network, like saving file in the cloud, etc. To do anything useful with this capability, we need network applications that use the network for providing services or performing computations. So again, the value of a network depends on how big it is. So your program or the function you create from your memory is only as valuable as the network it could connect to, as the service it could provide, as the computation it could provide to others. For example, when you're creating a YouTube video and having audience around the world, you're performing a lot of computation. You can think of that as performing a lot of computation to multiple networks around the world. Network applications are typically structured according to a small number of design patterns. So how are these applications, which is the actual program? Earlier we discussed the infrastructure from the ground up. Now, how does it look like, or how does the design pattern in the application layer point of view of the end host? So network applications are typically structured according to a small number of design patterns. The most common of these are client to server and peer to peer. So most network applications are designed so that one side is the client and the other side is the server. The server provides some type of service to clients, such as access to files on the server server host. So it can be read function to the server host. It can also be file uploads that is more sophisticated. But for example, on our website, our teleconsulting website, we allow them to read our website, to make a video call. So that's more sophisticated. So we can categorize servers into two classes, iterative and concurrent. So an iterative server iterates through the following steps: wait for a client request to arrive, process the client request, send the response back to the client that sent the request, go back to one. So that is inefficient because it doesn't support concurrency. Most of the application, even our application for a doctor app, allows concurrent user to request for a video call. So up until 100 concurrent users is the limit for us. So the problem with an iterative server occurs when step I2 takes a long time. So this because like I mentioned in the previous video, the creator of or the designer of these network applications are aware of operating system design principles, or the things that work that work in operating system. Therefore, they are aware of the um, they are aware of the concurrency that could be an issue with network requests as well. So here, the problem with an iterative server occurs in step 2, which takes a long time. So during this time, no other clients are serviced. So a concurrent server, on the other hand, performs the following step. Wait for a client request to arrive, start a new server instance to handle this client's request. Wait for a client request to arrive, start a new server instance. So it provide the server instance. So the analogy for this is with the previous video, which is the operating system. It creates separate threads or process. It instantiate a different process, and the other process are being handled by this multiprocessor system. Because remember, that server is still being operated by operating system to provide the administrative task for that hardware, right? So start a new server instance to handle this client's request. This may involve creating a new process, task, or thread, depending on what the underlying operating system supports. This new server handles one client's entire request. So this new server handles one client's entire request. When the requested task is complete, the new server terminates. So it allocates and gets that memory and that processor to be able to be free on executing other threads. Meanwhile, the original server instance continues to C3. So and then it go back to C1. So the advantage of concurrent server is that the server just spawns other server instances to handle the client request. Each client has in essence its own server, assuming that the operating systems allows multi-programming. Essentially all do today, multiple clients are serviced concurrently. Note that we use the terms client and server to refer to applications and not to the particular computer systems on which they run. So when we say client, it is in the 7th or application layer, not the entire and host layers. The very same terms are because that computer could have multiple clients and could have multiple servers. The very same terms are or that and host could have multiple servers and multiple clients. The very same terms are sometimes used to refer to the pieces of hardware that are most often used to execute either client or server applications. So this term sometimes used for a hardware that its entire purpose is to become a client, or sometimes a server, right? So some computer are just designed to be server, or some are just designed to be client. But your laptop or computer, though it is mostly client, it can also serve as a server. Okay, as a result, it is common to find a server in the hardware sense running more than one server in the application sense. So peer-to-peer, some applications are designed in a more distributed fashion when there is no single server. Some applications are designed in a more distributed fashion where there is no single server. Instead, each application acts both as client and as a server, sometimes as both at once, and is capable of forwarding requests. Now, sometimes, like one hardware could have multiple server instance that have that could be a client and a server at the same time, which makes it complex. So that's a peer-to-peer. Instead, each application acts both as client and server, sometimes as both at once, and is capable of forwarding requests. Now, also capable of forwarding requests, kind of like making the most. It is making more use of its resources of the end-to-end we discussed earlier than just the client-to-server application. So some very popular applications like Skype or BitTorrent are of this form. These applications are called peer-to-peer or P2P applications. A concurrent P2P application may receive an incoming request, determine if it's able to respond to the request, and if not, forward the request on to some other peer. So it's kind of like acting as a router as well if it need be. So this is taking the full capability of its end-to-end host. So that's what makes this application peer-to-peer. That's what we mean when we say that it also has a capability to route packets or to forward requests. It can be client and server at the same time. It can run a multiple client and server at the same time in a one computer, depending on the capability of the computer. Right? So thus, the set of P2P applications together form a network among applications, also called an overlay network. So, a set of these P2P applications together form a network among these P2P applications is called an overlay network. One of the primary problems in P2P networks is called the discovery problem. That is, how does one peer find which other peers can provide the data or service in a network where peers may come and go? So, how does it look, or how does it forward packets? How does it know where to forward packets? So this is usually handled by bootstrapping procedure, whereby each client is initially configured with the addresses and port numbers of some peers that are likely to be operating. So it is using this algorithm that use this IP address and port numbers of the peers that are likely alive in that network. Once connected, that new connection from that alive participant, the new participant learns of other active peers, and depending on the protocol, what services or files they provide. So based on that active or nearer, it could be near, or the currently active participant, what other participant doesn't know that it can forward the request. Application programming interfaces, applications, whether P2P or client or server, need to express their desired network operations like make a connection, write or read, write or read data. This is usually supported by host operating system using a networking application programming interface. So, just like a hardware needs an interface, an I/O hardware needs an interface to connect to the OS, or just like a software needs an interface or to provide an interface to be accessed by other software, a network application to be able to be connected or be accessed by other network device needs an application interface or programming interface. So this is usually supported by a host operating system using a networking application programming interface. So again, networking application programming interface. So this interface most resemble those networking application, or most those related to network. The most popular API is called sockets or Berkeley sockets, to mention where it came from. This text is not a programming, but occasionally we refer to a feature of TCP or IP and whether that feature is provided by the sockets. So these sockets are more resemble API programming text, but it's just needed here to be able to discuss how do we actually connect with other network devices from end to end. But we will not gonna discuss this further. So that's one of the uh, because in this set of protocols, we need to know if that features of TCP or IP in this set of protocols that could be supported in this protocol suite is whether it that feature is provided by the socket API, because it's still using API, kind of like the thread API, the malloc API that we discussed in the operating systems. All of the programming details with examples for sockets can be found in programming books. So modifications to socket intended for use with IPv6 are also described in a number of freely available online documents. So if your Wi-Fi supports IPv6, a modification to support that connection in the network are also provided online for free.